Okay, so a lot of you will know this, and some of you might even be CFD engineers who just interested in seeing what they do in F1. Uh, this is a, CFD pipeline. I never liked that term before, but I think it's the one that we recognize very widely. It's you can just divide it into three things: pre-processing, solving, and post-processing. Within those, obviously, there are quite a few steps which we'll get to slowly. So this is just an overview of what we'll be doing within these three parts of the pipeline of simulation. So we will then learn about CFD as applied in motorsports. We'll use some simple examples, as Shubham mentioned, but very nice, very cool. You can learn so much of the fundamentals with those simple examples. Uh, at every stage, we will ask, how is this particular thing done in F1? I think that's the nice bit. Uh, so within pre-processing, solving, and post-processing, you've got many steps. Each of those steps, we'll ask ourselves, how is this done in F1? Hopefully, we'll answer. And maybe the answer may be slightly outdated, and some of the answers will be very current. But I think the key thing is, how is it done in motorsports? How is it relevant to F1? And then I think that'll be quite interesting. Again, just to reiterate, the focus is on application of CFD. This is the scope of this workshop is not a deep understanding of the theory of CFD. So yeah, let's get started. So yeah, just a bit of a light a segue in. In 1990s, CFD started being used in a wide industrial sense because HPC hardware started being available, and some user-friendly software interfaces started being available. You can't imagine how it was before. But thankfully, I didn't have to do this really in the early stages of CFD. So when I started using, we already had pretty user-friendly interfaces. But yeah, I've had some colleagues who started a few years before that, and yeah, their experiences were really interesting. And where we are now is incredible. Even with OpenForm, you've got lots of uh, many open source user interfaces that will tie everything together for OpenForm in a nice graphical user interface. So how is safety used widely in the industry? It's used by vehicle manufacturers to predict aero performance. It reduces the lead time and cost of new designs, and I'm not talking about just of F1. In the automotive industry as well. You you get to study flow systems where controlled experiments are very complex and costly to perform. So, and I'm thinking of even just putting a normal road car in a wind tunnel as well. It's a fairly complex experiment just because it's a bluff body and not just an F1 car. And you get to analyze the results in the kind of detail that you don't experiment. It's not necessarily available experimentally, or if it is, it's very expensive. So those are the strong points: time and cost reduction for CFD. There is still untapped potential in HPC innovation. I think being out of F1 in automotive, I see almost the huge potential. I have that potential of HPC innovation in my group. It's readily available to us, and it's incredible. The limitations imposed on F1 teams is a shame because there can be a lot more that can be done in this field if it was open for F1. And then mathematical model evolution. So we've always had this problem. It's turbulence modeling. It's almost a Nobel Prize worthy problem. It hasn't been solved. But there's great evolution in that field as well. Fantastic research, and we'll touch upon that in some slides in the tomorrow possibly. So just a very basic introduction to mathematical models for fluids. Uh, I think we all know. Well, hopefully, a lot of us will know what this is. Navier-Stokes equation. So the conservation of mass, momentum, and energy. The three equations. These are the fundamental to describing the fluid dynamics problem. And what I'm trying to bring across here is we're not going to try and understand what this is. That's not the scope of this, but what we want to do is show what the simplifications of this set of equations are that's used in the industry. So what is used is we used going from a fully compressible and unsteady uh, formulation of the equations, we're going to an incompressible and steady state flow, and it simplifies to that. You take out the time parameter, and then also the density, because it's incompressible, and then you've got another formulation where you maintain you go to incompressible, but you keep the transient nature of the equation, so it's unsteady. You're solving unsteady flow. So the difference is you've got two things: steady flow and unsteady flow, and this is quite important to remember because we will talk about that tomorrow in a bit more detail. So fundamentally, those are the equations you're solving, and we'll start understanding a little bit more in detail how, why, what do we need to do to solve that, and all of those questions. So a CFD simulation requires the following fundamental steps. So you need to first discretize the domain and what is a domain? It's where it's all of the volume around the vehicle. So you need to discretize that into finite volumes. So that is the spatial discretization. And then we define boundary conditions and initial conditions, and then we define a numerical scheme to solve those equations that I just showed you. When what I've just described in words, when this is translated into a process, that's what provides us with this CFD pipeline, the famous thing. And that's the pre-processing, solving, post-processing with all of the details underneath each column. Um, as you can see, there's quite a few steps, and this is what a lot of the upcoming sessions today and then tomorrow will be talking about in detail about these steps. And some of this will be quite interactive. We'll look at some cases. We'll look at some solutions as well. But let's start with the one on the left. So this is pre-processing. We'll start with that. And I've just divided pre-processing into vehicle design, surface mesh, and volume mesh. And we'll pick this up in the next session. But just to give you an introduction to this, let's take this first one here, vehicle design. What are we talking about? What happens at this stage? So an initial vehicle design is made using either a CAD package or a styling studio software. And when I say that, it's because I now work in the automotive industry. I'm a bit more exposed to other packages where surfacing is done, like Alias, Blender, and other things. But in the motorsport industry, in F1 especially, cars are made in CATIA and X, CAD packages, basically. It is highly connected to the vehicle architecture, vehicle design. So when you, even in F1, when people start thinking of the next year's car, you start from the vehicle architecture. You start from where the powertrain is, where the cooling needs to go, where it starts from how the car is laid out in terms of its architecture, the bare bones of what makes the car go around the track or even move. And from there, then you start doing the rest of it. So that's the first step. And that involves a lot of mechanical systems that are completely critical to the car, and some of them are critical to a simulation as well. And we'll understand what some of these are. And then, as I just mentioned, this cooling system as well, the definition required of the cooling system for a vehicle. So that's what I mean by vehicle design. What we'll do is we'll talk about what F1 teams do, what's done in automotive industry, possibly more in detail later, but I've already mentioned a few things. Then the next step we'll talk about is surface meshing. So once you have the car designed in a CAD package or in some other package, for a CFD simulation, you then need to have a surface mesh that represents that surface of the car. So we'll discover that in a lot of detail and some case studies as well. The fundamental idea is that once you have the design of a vehicle, you prepare a watertight geometry for a CFD simulation, and it needs to have all the necessary detail that will accurately reproduce the effect of flow around the vehicle when compared to the real world. So you don't necessarily need to take every bit of detail, every nut, every screw, everything that is in the car. What I'm trying to get across is uh, what affects the flow, what is important, what gives you the accuracy of a result. That's what you need to consider in terms of the mechanical systems. Um, and then accurate representation of surfaces that bound the external flow. So what do I mean by that? Uh, you need to imagine where the flow is likely to go. It could be just around a car and not anywhere in the internals. But that's very unlikely because a car needs cooling, for example. So you'll have ducts involved that interact with the external airflow for cooling, for brakes, for engine cooling, and all of that. There'll be some internal mechanical parts that are wetted by the airflow as well. So, for example, air passes through the radiator, and then there might be a nice duct that brings it out, or it might just flow into the engine bay and then come out the back of the car. So you need to model. If that's what's happening, then you need to model those mechanical parts where the flow is touching. Uh, then there's tires and wheel internals. So you've got brake ducts. You used to have very complex brake ducts, so that's an important part. So these are the considerations you need when you're doing the two steps of vehicle design and surface mesh, because the surface mesh is a representation of the car that you've designed, but you're bringing it now to be ready for a CFD simulation. So you need to consider what is important for the airflow, and that's the key. Once you've described your surface simulation, then the next step is volume, generating a volume mesh. So what happens at this stage? We then discretize the volume around the car into volume cells because the mathematical equations that I showed you are applied on these cells as a simplification. And this is called spatial discretization of the CFD model. It constitutes of generating volume mesh cells. And an example of some of these cells are shown here, different kinds of cells. We'll talk about this a little bit later, why we would prefer a certain type of cells as opposed to others. We'll again at each stage we'll ask this question, which is quite important, and also we'll try and see what's done in the automotive industry, because it's always good to have a perspective of what's happening outside of F1 as well, because in some cases there are actually things that done outside of F1 that are more cutting edge, which we'll talk about briefly about them.